heat conduction problem or unsteady state heat conduction. Unsteady state means if the temperature of a body at any location is changing with respect to time, it is called unsteady state heat conduction. Till now, we have assumed that temperature at any location within a body is constant with respect to time. That is called steady state conditions. Whether it is in the fins or whether it is a heat generation case inside a slab or whether it is a heat generation in the case of the cylindrical wires or heat conduction through a composite slab or heat conduction through a composite cylinder or heat generation through a spherical container, hollow spherical container. In all these cases, till now we had assumed that steady state conditions are prevailing. That is, the temperature at any given location within a body is not changing with respect to time. But now, in this problem of unsteady state conduction or transient heat conduction, we assume that temperature could change with respect to time. Unsteady state means temperature of body at any location could change with respect to time. Mathematically, temperature is a function of tau. Tau means time. Time in seconds. The solution of any unsteady state problem is much more complex than that of the steady state one because of the presence of the variable that is time t. Now, for example, I do consider a small simple problem regarding the temperature variation with respect to time and as well as the distance within the body. Let us do a simple problem as an example. The temperature distribution across a large concrete slab 50 centimeters thick, heated from one side as measured by thermocouples approximates to the following relation, that is T is equal to 60 minus 50x plus 12x square plus 20x cube minus 15x to the power of 4, where T is in degrees Celsius and x is in meters. Considering an area of 5 meters square, compute number 1. The heat entering and leaving the slab in unit time. Number 2. the heat energy stored in unit time. Number 3, the rate of temperature change at both sides of the slab. Number 4, the point where the rate of heating or cooling is maximum. For the slab, we can take K is 1.2 watts per meter Kelvin thermal conductivity, and thermal diffusivity alpha is 1.77 into 10 power minus 3 meter square per hour. The solution to this problem could be given as, here T is given as 60 minus 50x plus 12x square plus 20x cube minus 15x to the power of 4. Therefore, dou T by dou X, the rate of temperature change with respect to X, is minus 50 plus 24x plus 60x square minus 60x cube. Dou square T by dx square, if you differentiate it again, 24 plus 120x minus 180x square. Therefore, first thing is Q, the rate of heat entering the slab or leaving the slab at unit time, for which I have to use the Fourier law, minus Ka dou T by dou X, that is minus Ka minus 50 plus 24x plus 60x square minus 60x cube. It is from Fourier law. If we substitute here dou T by dou X at x is equal to 0, we will be getting the heat entering the slab. If you substitute x is equal to 0.5, that is the width of the slab, we will be getting the heat leaving the slab. So, heat entering the slab is equal to Q at x is equal to 0 is equal to minus Ka dou T by dou X at x is equal to 0, that is equal to minus 1.2 into 5 into area is already written 5. Dou T by dou X at x is equal to 0, we would be obtaining as minus 50. That gives you 300 watts. Similarly, heat leaving the slab is equal to Q at x is equal to L. We can say that is, if this is given as the slab, here x is 0, here x is 0.5. This is heat is entering, here heat is leaving. Here Qx is equal to 0, here Qx is equal to L. Qx is equal to L could be obtained as minus 1.2 into 5 minus 50 plus 12 plus 15 minus 7.5, that gives you 183 watts. Therefore, the rate of heat storage is equal to heat entering minus heat leaving, that is 300 minus 183, this becomes 117 watts. Now, if you look at the dou t by dou tau or dou small t, that is where tau is the time, alpha into dou square t by dou x square, that is alpha into 24 plus 120x minus 180x square, where alpha is the thermal diffusivity. To get the rate of temperature change at both sides of the slab. Therefore, dou t by dou tau at x is equal to 0, that is rate of temperature change at the x is equal to 0 will be obtaining as 1.77 into 10 power minus 3 into 24, that is 42.48 into 10 power minus 3 degrees centigrade per hour. Similarly, the rate of temperature change at x is equal to L is 1.77 into 10 power minus 3, that is alpha. Put x is equal to 0.5 in this equation, the above equation. We will be getting 69.023 into 10 power minus 3 degrees centigrade per hour. Because if you take one-dimensional heat conduction, dou square t by dou x square is equal to 1 by alpha plus q dot by k is equal to 1 by alpha into dou t by dou tau. Here no heat generation, q dot is 0. Therefore, dou square t by dou x square is into alpha is dou t by dou tau, where this is the rate of temperature change with respect to time. Last one, for the rate of heating or cooling to be maximum, dou by dou x of dou t by dou t is equal to 0 or tau. I can write small t or capital or tau for time. It becomes alpha into dou by dou x of dou square t by dou x square or dou cube t by dou x cube is 0. That is 120 minus 360 x is equal to 0 implies x is equal to 0.33 meters. That is, at a distance of x is equal to 0.3 meters, we will be getting the rate of location where the rate of heating or cooling of the slab is a maximum. So in this problem, the actual thing what we have to understand is, because of the heat conducted at x is equal to 0, or heat entering the slab is more than the heat leaving the slab, that is at x is equal to L, there is heat stored within the slab, because of which the temperature of the slab keeps on increasing with respect to time. Here the dou t by dou tau or dou t by dou small t shall indicate the rate of change of temperature of the slab with respect to time at any location. It is not same. The rate of temperature change with respect to time is changing with respect to x again. If you look at x is equal to 0, the rate of temperature change is 42.48, whereas at x is equal to L, it is 69.03. That means at x is equal to L, the slab is getting cooled faster than the at x is equal to 0. But the rate of cooling or heating is maximum, in fact, at a location of x is equal to 0.33 meters measured from x is equal to 0, where the temperature changes are maximum. Quickly the temperature is changing at x is equal to 0.33 meters. So as a whole, what we have to understand is, here the unsteady state conditions are prevailing. That is, temperature at any location within the slab is not constant. It is changing with respect to time. At some locations, the change is much more than at some other locations. Hence the problem. Now, I shall deal with unsteady state conduction with negligible internal conduction resistance. It is also known as lumped heat capacity analysis. Very important in the gate point of view, because in the gate there are a number of problems are being asked about this. Lumped heat capacity analysis. Now I shall consider, the problem goes like this. I shall consider a small body of mass m, volume v, density rho, specific heat Cp. M is mass of body in kg, V is volume of body in meter cube, rho is density, which is given in kg per meter cube, obviously. Cp is specific heat of body in joule per kg Kelvin. Let this body is at a initial temperature of Ti. When it is suddenly quenched or exposed to an environment whose temperature is T infinity. It is environment T infinity. This body is suddenly exposed to this environment at T infinity when the temperature of the body is Ti. Let Ti be the temperature of body when it is suddenly exposed to the environment at T infinity. The body starts losing heat by convection to the environment with a convection coefficient of H. Let H is equal to convection heat transfer coefficient between body and fluid in watts per meter square Kelvin. So the temperature of the body keeps on decreasing with respect to time. Let T be the temperature of body at any instant of time, tau seconds, measured from tau is equal to 0 when the temperature of body is Ti. Ti is initial temperature of the body at the time tau is equal to 0, whereas T be the temperature of the body at any instant of time, later time, tau seconds. Now T is a function of tau. The temperature of the body is a function of time. T is in degrees centigrade, tau is in seconds. Now writing the energy balance equation at that instant of time t seconds, tau seconds, tau seconds otherwise. The rate of convection heat loss from body to fluid is equal to the rate of decrease or change of internal energy of body with respect to time. The rate of convection heat loss from the body to the fluid is rate of decrease in internal energy of the body with respect to time. That is the energy balance or first law of thermodynamics. Hence, the rate of convection heat loss is HA T minus T infinity, where A is the surface area of the body, is equal to minus sign being written that temperature of the body is decreasing because the body is losing heat by convection to the fluid. That is d by d tau of mCp T, where m is the mass of the body, Cp is the specific heat of the body, and T is the temperature of the body. So many joules per second. Minus d by d tau of mass is replaced with density into volume. So many joules per second. Now, if you look at this equation, H, comma, A, comma, rho, comma, V, comma, Cp, all are constants. There are only two variables. Temperature is a function of time. Separating the variables, that is T and tau, we get d tau is equal to rho V Cp by HA dt by T minus T infinity minus. So, time on one side, temperature on the other side. Now, integrating integral d tau. What are the limits of time? 0 to any instant of time. Tau is equal to minus rho V Cp by HA into dt by T minus T infinity. What are the limits for temperature? At tau time 0 seconds, the respective limits of temperature are Ti to T. Please note that here tau is time. And remove the minus and you can interchange the limits, and also the constant rho V Cp by HA can be taken out. Please note that here A is surface area of body in contact with the fluid, and integral Ti to T dt by T minus T infinity. Therefore, implies tau is equal to rho V Cp by HA ln Ti minus T infinity divided by T minus T infinity, implies Ti minus T infinity divided by T minus T infinity is equal to e to the power of tau into HA by rho v Cp. So this is the function between T and tau. So at any time tau, we can calculate temperature T, and to reach the temperature T, what is the time required, tau, that also could be calculated. So this is the temperature variation of a body with respect to time, tau seconds. Or it could be even written as T minus T infinity by Ti minus T infinity. Ti is the initial temperature, is e to the power of minus HA by rho v Cp into tau. Tau is the seconds. This is the temperature variation with respect to time under unsteady state condition or lumped heat capacity analysis of the body. This analysis is also called as lumped heat capacity analysis, in this it is assumed that the temperature throughout the solid at any instant of time is same. That is, thermal conductivity of the body, whatever we are considering, should be of very high value, and the size of the body is of very small. And the thermal network for the lumped heat capacity system is shown here. It is the capacitor connected in parallel to the resistance. Thermal capacitance is given by rho Cv, or mass into specific heat. Here we should notice that the thermal capacity of the system is charged initially at the potential T0 by closing the switch S. Then when the switch is opened, the energy stored in the thermal capacitance is dissipated through the resistance 1 by HA. Here the thermal system and electrical system are analogous. So we could construct an electrical system like a thermal system as long as HA by rho v Cp is equal to 1 by thermal resistance into thermal capacitance, where thermal resistance is 1 by HA, thermal capacitance is rho Cp into volume or mass into specific heat. Thermal resistance is 1 by HA and thermal capacitance is mass into specific heat. The flow of energy in the thermal system is heat, and the flow of charge is equivalent called as electrical current. The quantity rho v Cp by HA is called time constant because it has the dimensions of time, that is second. In fact, this analysis, also known as lumped heat capacity analysis, in which the temperature of the body is only a function of time and not a function of space, is applicable under one certain condition, where the Biot number of the body is less than 0.1. Here I shall define the Biot number. So the criteria for lumped heat capacity analysis is Biot number should be less than 0.1, where Biot number is given by Hs by K, that is S by Ka divided by 1 by Ha, that is internal conductive resistance divided by external convective resistance. So S is given as volume of the body divided by area, surface area of the body. It has got a linear dimension Cm. So S by Ka is internal conductive resistance and 1 by Ha is external convective resistance. Only when the Biot number is less than 0.1, lumped heat capacity analysis is valid. That means when the body is of very small size and the conductivity of the body should be of a very high value, like copper ball or a silver ball or a aluminum ball. Only for a small bodies and of high conductivity bodies, this analysis of lumped heat capacity is valid. That is when the Biot number is less than 0.1. This is the criteria for lumped heat capacity analysis. The body should not offer any internal conductive resistance. There must be resistance only at the surface via convection heat transfer between the surface of the body and the fluid. This is the lumped heat capacity analysis.